Alright, in this example, we've got a closed interval from -1 to 3. We want to find our first derivative. F prime of x equals 2 minus, I'm going to have 2/3 times 3. So that's going to be 2x to the -1/3. And I want to find out where this derivative is equal to 0 and where it's undefined. And it's much easier, and this is in my opinion, to rewrite these as fractions and combine them into one. When you have a fraction, I think you can visualize better where the function is undefined. So I'm going to write this as 2 minus 2 over x to the 1/3. I need to have a common denominator. I want to multiply this term by x to the 1/3 over x to the 1/3. Come up here. So I'm going to get my first derivative is equal to 2x to the 1/3 minus 2 all over x to the 1/3. And I know that f prime of x equals 0 when 2x to the 1/3 minus 2 equals 0. If I factor out a 2, I get x to the 1/3 minus 1 equals 0. Solving, I get x is equal to 1. And that is an interior point on this function. Okay. I also want to find out where the first derivative is undefined. And the first derivative is undefined when the denominator is equal to 0. And so the denominator equals 0 when x equals 0. Both of these values, 1 and 0, are on our interval. And so I know that on a closed interval I'm guaranteed to have an absolute max and an absolute min. I know that if I have an absolute max and an absolute min, that they have to occur at either endpoints or at critical values. And so I'll test -1, 3, x equals 1, and x equals 0, all in the original function. Right? The first derivative's purpose here is to give us the critical values. The original function is going to give us the actual absolute maxes and absolute mins. So we're going to put our original function in the calculator so that we can evaluate our critical values and our endpoints. And we've got 2x minus 3x to the 2/3. Again, we can use a table or we can use the vars key. Let's go back into the table and we'll clear out what we used from the last problem. We'll hit -1, 3, 0, and 1. That's our last value to test. So looking at this function, we can see that this table, that -5 is the absolute min and 0 is actually the absolute max. This was the way calculus was used to find maxes and mins, and now we have ways of graphing. The way that I look at this is that the screen doesn't tell the whole story, and so it's the calculus that helps us confirm what the calculator is telling us, or vice versa. If I find the absolute max and min analytically, I can use the calculator to kind of check my work. So we can graph this. And I'm just going to do a zoom 6. Here's our function. I'm going to trace on 0 and I'm going to zoom in. And I want to make sure in my window that I have at least from -1 to 3. I have -1 right here, but let's make sure we have 3 as our maximum x. Let me put 3 in there, and then we'll graph this. Right, so we can see here when we found those critical values, we found 1 at x equals 1, and then when I trace on 1, I can see I've got a horizontal tangent. I found that the first derivative was undefined when x equals 0, and if you trace on 0, you can see you've got a cusp. And then the endpoints, I can just trace on those. If I trace on -1, which is an endpoint, I can see my value is -5. And if I trace on 3, I can see that my y value is -0.2403, rounded out to 4 decimal places.